is Tobias Pfannzelter, and I'm presenting tinyFaaS, a lightweight FaaS platform for edge environments, as a recorded presentation for this year's International Conference on Fog Computing. Function as a service is the newest evolution of sharing in cloud computing. Whereas in virtual machines, only underlying hardware is shared and tenants manage their own virtual machine stack, in function as a service, or lambdas, all tenants share hardware, operating system, and runtime, and each manage their own app. Everything but function code is managed by providers. A typical FaaS platform receives incoming events, forwards these events into an isolated environment where the tenant's function code is running, and if that function code provides any output, forwards that output to where it needs to go. The Internet of Things can leverage many of the advantages of function as a service. For example, the IoT can benefit from automated scaling through stateless functions. Microservice architectures that are based on combining many functions are flexible and can easily be adapted to the ever-changing requirements of the IoT. As everything but the function code is managed by providers, tenants can benefit from low maintenance overhead. And finally, the event-based programming model of functions as a service fit the IoT. Let's look at a typical fog infrastructure. There are 4 layers. In the center, there are powerful cloud nodes, then there are intermediary fog nodes, and finally there are edge nodes such as gateways and the actual IoT devices. Let's say that a function is deployed in the cloud. There are 2 devices that want to use this function. One is an event source, which produces an event. In this case, we have an IoT device. The target is a device that needs to be managed according to the events produced by the first device. Events are sent to the function in the cloud, transformed by the function, and sent to the target device at the edge. This, however, introduces latency, requires additional bandwidth, and leads to inefficient resource allocation. What if we move the function to the edge? Because processing IoT data close to the edge can reduce latency, reduce bandwidth consumption, and increase resource efficiency. There are few existing approaches to function as a service at the edge. Platforms such as AWS Greengrass and Azure IoT Edge are lightweight and can use IoT protocols such as MQTT. However, they are proprietary and cannot be extended to cover custom devices, custom use cases, and so on. Open source function as a service platforms such as OpenWhisk, Knative, and Kubeless are extensible and can cover custom use cases, which is especially important in the IoT, but they are very complex and heavyweight, and as such not fit to be installed near the edge where resources are limited. Finally, there's Lean OpenWhisk, which is a deployment option of OpenWhisk that removes some complex components, making it lighter, yet still too heavyweight to be installed in very constrained environments. A function as a service platform at the edge should support lightweight messaging protocols used in the IoT, run on heterogeneous hardware, have very low hardware requirements, be built with network and hardware constraints in mind, and be extensible. We present tinyFaaS, a function as a service platform that is fit for the edge. tinyFaaS is a custom and extensible function as a service platform. There are three main components to tinyFaaS. There is a reverse proxy that accepts incoming requests. There are function handlers for each function that is installed on tinyFaaS, and there's a management service that manages function handlers and endpoints. Let's start with the reverse proxy. The reverse proxy accepts incoming co-op requests. Requests are forwarded as HTTP requests to their corresponding function handlers. Once the proxy receives an answer from the function handler, it sends that answer as a co-op response to the client. Choosing the correct protocol for client communication is very important. While traditional function-as-a-service platforms often provide HTTP endpoints, which is useful for web-based services, in the Internet of Things, which is important for us at the edge, other protocols may be superior. The advantage of using co-op is that it uses significantly less bandwidth and induces less latency. Furthermore, power consumptions and resource requirements on both the platform and client side are significantly lower. At the same time, as it is request-response based, co-op is conceptually similar to HTTP. Co-op is very lightweight. It uses UDP at the transport layer instead of TCP. It is compatible with HTTP and RESTful APIs, and it is stateless, which is useful for all stateless functions. However, it is very young, having first been introduced less than 10 years ago, and because it uses UDP, it has low reliability and quality of service. Next are the function handlers. For each function that a tenant deploys on a platform, a function handler is created. Function handlers have two components. First, there's an HTTP server that accepts incoming HTTP requests from the reverse proxy. For each request, function code is executed. As you can see, each function handler can process many requests at the same time. Requests are only isolated between functions, not between requests to the same function. That means that each function handler can process many requests at the same time. To ensure isolation, each function handler is deployed as a dedicated Docker container. Function handlers can only communicate with the reverse proxy, not between each other. This is ensured by using dedicated Docker networks. To implement a new function runtime, the runtime only has to provide HTTP compatibility. It means that new function runtimes can easily be implemented as long as HTTP servers within a Docker container are available. Reusing existing containers to process function calls dramatically increases resource efficiency, as the overhead from Docker is limited. Next is the management service. The management service communicates with the reverse proxy to create and remove endpoints. It communicates with the Docker daemon that manages the handlers to create and remove new function handlers. It also provides an endpoint for tenants to create and remove functions and update function code. To evaluate our design, we have implemented a proof of concept. We have deployed our proof of concept on both a single board computer and a cloud server. We have then benchmarked and compared our deployments to state-of-the-art platforms. There are three parts to our proof of concept implementation. The reverse proxy is implemented in Go 1.13 using the Go core library and standard libraries. The management service is implemented in Python 3 using the Docker Python library. For our proof of concept, we have implemented a function handler for Node.js functions using the official Node Docker image. Our proof of concept implementation is available on GitHub as open source software. We have made two different deployments. To evaluate whether our platform runs on heterogeneous hardware, we have chosen to deploy tinyFaaS on both a constrained single-board computer and a larger, more powerful cloud server. We've chosen a Raspberry Pi 3B Plus as our single-board computer, quad-core ARM processor, 1 GB of memory, and 100 MB per second network uplink, and an EC2 M5A large virtual machine on Amazon AWS. This virtual machine has two virtual CPUs, 8 GB of memory, and a 10 GB per second network uplink. For our benchmark, we have deployed an exemplary function to tinyFaaS. This exemplary function implements the ICFC testers that calculates prime numbers between 1 and 1000. We have also created a benchmarking client. This client follows a closed workload model. There are several client threads. Each thread picks an operation from the operation pool, sends a request to the function as a service platform, and can either receive a response or timeout. The client thread will then pick a new operation from the pool. Next to our platform, we evaluate three other approaches. First, there's the native Node.js function. We attach a Node co-op server directly to our exemplary function. Then we also deploy Lean OpenWhisk on our systems. And finally, we also deploy Kubeless as a function as a service platform. And these are the results. Results for tinyFaaS are shown in light gray. We show our results as a cumulative distribution function. As you can see, on the Raspberry Pi, latency for requests from tinyFaaS is close to that of native performance. Lean OpenWhisk, on the other hand, is not usable with more than one client thread at a time. It is, as such, infeasible for smaller, more constrained systems. Kubeless introduces some overhead and fails especially when more client threads are used. On our cloud server, results look largely similar. Again, tinyFaaS has performance that is close to that of native Node.js, although it still introduces some small overhead. Lean OpenWhisk's overhead is bigger compared to tinyFaaS. Kubeless can achieve better performance, up to 16 simultaneous client threads. However, with more than 256 threads, performance is lowered drastically. Here, Kubeless failed to answer more than 50% of requests. Performance of Lean OpenWhisk is similar. Again, it works for up to 16 simultaneous client threads. With more than 256 threads, Lean OpenWhisk becomes unusable, even on the larger cloud machine. I have introduced some requirements for a fast platform at the edge. tinyFaaS, by using CoAP, supports lightweight messaging protocols used in the IoT. We have shown in our evaluation that tinyFaaS runs on both a cloud server and constrained single-board devices. As such, hardware requirements are very low and overhead is limited. We have also shown that we have built it with network and hardware constraints in mind. And finally, by using a modular, flexible design, it can easily be extended. For example, a new language runtime could be implemented by simply building an HTTP server within a Docker container in that language. To conclude, our motivation was that serverless is a promising paradigm for the Internet of Things. However, current function-as-a-service platforms are not suitable to be run everywhere on the edge. We have presented tinyFaaS as a solution. It is lightweight and made for single-node systems, leveraging co-op and intelligent sharing of function containers. In our evaluation, our proof of concept implementation had very little overhead compared to native, was significantly faster than existing FaaS platforms, notably than Lean OpenRisk, and it scaled better than existing FaaS platforms. If you have any questions or would like to see the prototype, please refer to our website or my email address. Thank you for your attention.